we'll also understand this. When there are system of forces acting on a body, all can be reduced into force and a couple at another point. So this can be brought to this O, and then you have to introduce a couple which is equal to the moment of this force about this point. Similarly for this force, so this is equal to, I'm moving all the forces to this point by introducing the couple at that point. So the net effect of these forces on this body is unaltered. Finally, we know for all the forces there's a resultant force. For all the couples, we have a resultant couple. So we sum all the force vectors, and we sum all the coupled vectors. That is what is given here. So this is also can be understood. Find all about a point. Now to transfer to another point, we have to write this vector expression to find out the effect of the force on another point. Reduction of a system of forces. Okay, these all are equal. Okay, as we saw that in the previous slide, we take the three forces acting on a body which is in a plane. Okay, so for all these forces there will be a resultant. Okay, that resultant will be acting some other place. We are moving that resultant to O. Then we have to introduce a moment of that resultant about O. So that is given. So now these three forces reduced into a resultant force. That force is moved to O, thereby introducing, or by introducing a couple, the effect is unchanged. And it is also equal. Now, how to remove this moment? We have to write, because we know moment equal to force into perpendicular, that distance. So distance between the force to the O. So if we know the distance on which the line of action of the resultant is acting, if we move this vector to that distance, the moment is released, because moment is force into distance. Now distance we are finding out, moment divided by the force. So find the distance and put the force. Now where you may have a question from here, should we move this direction or this direction? That is because that is based on the sign. It is anti-clockwise, definitely it has to be moved right this side, because about O this will produce anti-clockwise moment. This R will produce anti-clockwise moment about O. Now this can also be reduced into components. You can split into components Rx, Ry. We can also write this way. Now we can move this in X axis alone or Y axis alone. So if you are moving this in X direction, the X distance has to be found out. We are moving to X distance. This is called, this point P is called X intercept. Similarly, this can be moved to Y, so that you can remove this moment, so, or the couple. Now we have to find out the Y intercept, where at Y these components are acting such that the net effect is not changed. That is the intercept point. This is the X point where you put the resultant force, so that the net effect is unchanged. All these are equal. In any form, you can write and solve the problems. We also solve this problem, one typical problem, how to reduce the forces and introduce couple. So this is one typical problem we'll solve now.
Let us now discuss a very important problem which will help us to understand the force coupled system properly. See this problem. A ocean liner is kept in its pier using 4 tugboats. A normal passenger ship, a big ship, is placed in the pier using the tugboats. Now, in this problem, it has 2 parts. The question has 2 parts. The first part is, all the 4 tugboats are exerting 5000 Newton force on the ocean liner. Now, it is exerting force about this point O, called the foremast point, where the mast, big column like spars are mounted, and that is one point. About this point, what is the force coupled system here? That is the first part, or equivalent force coupled system. Second thing is, there are 4 boats used. If at all we have to use only one tugboat, a bigger one, okay, in the hull, the surface, if you see this is hull, this is hull. On the surface, where the bigger boat has to apply, or where it has to exert the force, such that producing the same effect of all these 4 boats. This is the question. Okay. So now, all these tugboats are exerting 5000 Newton force. So this is 5000, this is 5000, this is 5000, and this is 5000. But these forces are inclined and the distances are given. All these distances are in meters. Fine. Now, we know how to resolve these components, the force components. So, first I resolve this into horizontal and vertical component. So, this is the location and horizontal component and vertical component. Okay. So, 5000 cos 60, 5000 sin 60. This one is here. Okay. And what is this? It represents the inclination. Okay. And if this is theta, right, and the hypotenuse is 5. Okay. So the horizontal component and the vertical component, the horizontal component is 5000 cos theta. Cos theta is adjacent by hypotenuse. So into 3 by 5. The vertical component is 5000 into 4 by 5. Now it is a vertical force, so you can directly that 5000, and now this force horizontal is 5000 cos 45, vertical is 5000 sin 45. Both are same values, by the way. Now we have resolved all the forces. About this point, we have to find the equivalent force coupled system. So now you see here, maybe this values cos 60 is 0.5, so this happens to be 2500, and this value is 433.13. So this value is 3000, this is 4000, so this is 4000, this is 3000, and this is 3535.5, 3535.5, this is 3535.5. Okay, so this O point is placed here. Both are the same points. What I am going to do, I am going to bring the force here. If I have to bring a force to another point, I have to introduce a couple which is equal to the moment of that force about that particular point. We know that. So each of the forces, this is 1, 2, 3 and 4, totally we have 7 forces. Okay, we have to bring all the forces to this point, so all the forces will produce a moment as well. So we will introduce a couple which is the moment in that point. So I am doing it, this exact point I am bringing here. So we will see. I am going to first take this force, horizontal force, this is 2500. Okay, I am placing that. So this is 2500. Okay, the vertical force downward 4330.13. Okay, now you see, when this 2500 is moved here at O, what we need to do? We have to introduce a couple. So what is the couple that we are going to introduce here, which will be the moment of this force about O? Okay, I am placing all the couple here, all the forces here, in order to make you clearly see each couple and its direction, each force and its direction. Actually, both are the same points. Okay, so this will produce a couple about this point. So the 2500 into the perpendicular distance. Which is the perpendicular distance? This is the perpendicular distance. How do you see that? The line of action of the force, okay, and you draw another line which is passing through the point O, and the least distance between those two lines is the perpendicular distance. So the perpendicular distance for this force is 15, and you keep your finger like this and forget about all other forces. Just look at this force, just push it, then the body will rotate in a particular direction, either it is clockwise or anti-clockwise. So when I am keeping my finger here and looking at this force, this is going to rotate the body like this, so it is going to produce a clockwise moment. So that clockwise I am placing. What is that magnitude? 5000 into 15. Now I am taking this force, I have placed it here. This will produce a moment when you are keeping your finger and move this force, it is going to produce anti-clockwise moment. So for an anti-clockwise moment, the value is 4330.13 into, what is the perpendicular distance? The line of action, okay, and this is perpendicular distance, that is 27, 4330.13 into 27. Now we will come to these two forces. There is a horizontal force towards right. I am placing it here. Actually it is acting only here, but in order to clearly see the force, I am drawing here. So that is 3000 Newton. And it will produce a clockwise moment. So there is a clockwise moment, 3000 into the perpendicular distance is 21. Okay, and you see this force, it is 4000 Newton, it is vertically downward, it is 4000, okay, and it will also produce a clockwise moment. So 4000 into the perpendicular distance is 30. Right? Now, you take only this force, it is a vertical force, okay, vertical force downward 5000, and it is also producing a clockwise moment. The perpendicular distance is 120. So I am placing it over here. The magnitude is 5000 into 120. Right? Now we have two more forces. This is towards right. Okay, I am placing it here. So 35.5, and it will produce about this point, it will produce an anti-clockwise moment. It will produce an anti-clockwise moment. So that is, the value is 3535.5 into 90. Sorry, 21. Horizontal force. The vertical force will also produce an anti-clockwise moment, but the force is upward. So that is 3535.5, and it is producing anti-clockwise moment. Okay, so the value is 3535.5 into the perpendicular distance is 90. Okay, so a lot of values are there. I am going to make it in a tabular column. Let me write each values. I am going to write all the horizontal forces. Towards right is positive, towards left is negative. Here no left side force is present, so I am going to place each force here. So 2500 plus, and then the vertical force 4330.13. Okay, let me write the values. So the clockwise moment 37,500 negative. Okay, and then you have anti-clockwise, right? 4330.13 into 27, which is plus 6913 0.5 all or Newton meter. You can use even in kilonewton. You can calculate using kilonewton also. The values will be smaller one, so that is also good. Okay, now the next force is 3000 and 4000. So I am writing this 3000 plus and 4000 minus because downward is negative, and we have 3000 into 21, 4000 into 30. So 3000 into 21 minus 63,000, 4000 into 30, that is minus 1,20,000. Okay, this force is vertical force 5000. Okay, minus 5000. For 5000 you have only one moment. Okay, that is 5000 into 120. It's nothing but 6 lakhs. Okay, lastly these two forces. So one is 3535.5 and this is also plus 3535.5, and we have two moments 3535.5 into 21, that is 74,245. So this value is for 90 into 90, and for 3535.5 into 21 we have 3181.95. Both are positive. What have I done? I have brought all the forces to this 4 mass point. Okay, all the forces, the corresponding moments. Okay, so this is the first force, these two forces and the corresponding moments. These two forces and the corresponding moments. So here this is anti-clockwise, so it is positive. All these three forces are clockwise, so it is negative. And then we have one force, that is 5000 vertical downward, that is why these are negatives, and we have one moment by this 5000 force, 5000 Newton, that is given here, and then these two forces are there, and it has horizontal positive, vertical positive because it is upward. Okay, and the corresponding moments. Okay, this is the vertical moment, this force producing anti-clockwise moment, and this force producing an anti-clockwise moment. So if you are able to write all this in a table form, you will not make calculation error. Okay, now what we have to do? We have to sum all the horizontal forces, vertical forces. We have to add all the couples. Upon adding 9035.5 minus 9794.63 minus 31146. A small calculation error might be there. Please take care of that while calculating. See, okay, how you are calculating the values. Fine. Now you see, what does it mean? the resultant in x direction is positive, the resultant in y direction is negative, and what does this mean? It is the resultant is a clockwise moment or clockwise couple. Okay, so now what is the first question? We have to find equivalent force coupled system acting here. Okay, so replacing all these forces, we have to place only one single force and a single couple. Okay, see here, this is 9035.5 and 9794.63. Okay, find out the resultant. The resultant happens to be, how do you find out the resultant? Square plus square under root will give you the resultant. So 13,325.73 Newton. This is the resultant. Okay. The couple that is acting is clockwise. 3,111.46. Okay, so now you see here, this is the resultant force that is acting here. What is the inclination? Inclination is theta equal to tan inverse summation of Fy by Fx, summation of Fx 94.63 divided by 9035.5, you get 47.3. To the horizontal 47.3 degree. Okay, so now that is what is acting here. We have obtained it, the resultant of all the forces and the resultant of all the couples that is acting. So this is one part of the question. So 311.15 kilonewton meter, and the resultant is 13.3 kilonewton. Fine. This is first part. Now the second part is more interesting and important. Okay. Now we have already learned, if you could see the previous slide, okay, we discussed how all these forces could be written. Okay. So we can write like this. Now if at all to release this couple, we have to move this force, the line of action of the force, the inclination will not change, but it will move away, either right side or left side based on the direction of the couple. So then we can release this couple. Okay. Now the second question is, where on the hull a single larger tugboat is forcing to keep the liner or the ship in position in its pier? That is the question. So replacing all four tugboats, we are going to use only one tugboat. Where I have to place it? Okay. So the resultant, okay, where it will act. Okay. Let us see that. If I have to release this couple, my force is this side, it will produce a clockwise couple. If I am moving this resultant this side, it will produce an anti-clockwise couple. So I have to move this resultant to some distance d such that I will get a line of action. On that line of action, if the single bigger boat is exerting the force, then it is producing the same effect of all these 4 boards. Okay, so now how to find that? We have a straightforward formula: moment equal to force into distance, so distance equal to the couple by force. So the couple is 311.15 by force is 13.3. So I get the dimension D as 23.34. So 23.34, what is that? Meter. Okay. Now what am I going to do? I am replacing this couple. I am replacing this force. Where I am going to place? From here, this line of action, initial line of action, that is this angle, 47.3. 47.3, that angle cannot be changed, but the force will move. Okay, so a parallel, this is the line of action of the resultant force. Okay, this is the direction. Okay, this is the distance. Right. So in this line of action, you know the direction of the resultant. Either I can place a boat here, or I have to use a boat and pull it. Either you use a boat here to push it, or you place the boat here and pull it. The net effect, principle of transmissibility, the net effect will not change. Okay. So now, but what is asked? It can only act at the hull, only on the surface. So what I have to find is this coordinate point. This point where I have to place my bigger boat. Okay. So this x and y is 21 meters. This x meter I do not know. Okay, fine, right. Now how to find this x? I have different methods. You can use vector method to find out the x straight away. The position vector cross force vector is equal to moment vector, so you can directly get the x component there. So x you can directly get. Now I am going to use another method where what I am going to do, see the previous slide, you can find, so you see this resultant, this x component, y component, you can place here, this couple is acting here, so the components are there. Either I can move, right, to release the couple, I can move in x axis or x direction in the same line of O in x direction, or I can move in the same direction, y direction from O. If I move that, also the couple will be released. Okay, so that is called the x intercept and the y intercept. Please refer to the previous slide. Okay, now this is the x intercept, ixi, and where is my y intercept? This is my y intercept. How do you find that? Okay, x intercept can be found. Okay, I'll erase all this for better clarity. Okay, this is x intercept. So now if I move this here, these two forces here towards right, the x component will not produce a moment. The y component 9794.63 will contribute for the couple. Okay, and and it will produce a clockwise couple. So the x component will not participate because it is passing through O. It will not produce a moment. Now this distance is x. So x I call it I because we have another h. So x intercept is moment. Moment is 311.15 divided by only the vertical force component. Okay, so 97.95. So the x intercept is 31.77 meter. 31.77 meter. Right? Now what is y-intercept? Y-intercept is moment by, so the x component will contribute for the moment and the y component will not produce a moment. Okay, so the x component is 9035.5. So this will produce a clockwise moment. So if you release these components to this point, the couple is, if you move these components from here to here, the couple is released, right? So 90.36, the y-intercept is 34.44 meter. Okay, now actually I need only this distance. This is my x distance. I need only this, right? So you can use similar triangle. This is a triangle, this is a triangle. Okay, you know this distance, you know this distance, and you know this distance, so you have to find out only this distance. Okay, I have exaggerated that so that you can understand. This is the hull. This is the hull where I am going to place my tugboat. Okay. A. So A by 31.77 equal to 21 by 34.44. Right. So A will be equal to 19.37. So this is 19.37. So then what is this value? 31.77 minus 19.37 is 12.4 meter. 12.3 something or close to 12 point. So if this x is 12 point or 39 or 4 comma 21. So this is x and this is y. We have found that. So from the foremast point, if the single bigger tugboat is used, what is the resultant force that is acting there? The resultant force will be 13.3 3 kilonewton. So 13.3 kilonewton force is acting, okay, in this line of action. What is the inclination? The inclination is, this inclination is 47.3. So this inclination is 47.3. So this inclination to the horizontal is 47.3. This inclination, if this single boat with this force can produce the same effect of all these 4 tugboats. Okay, quickly I will summarize. There are 4 forces acting. The inclined forces are resolved, and then the first part of the question, okay, what is the equivalent force coupled system for all the forces acting? There are 7 forces. All the 7 forces has to be brought to this point, and when you are shifting the point of application of the force, you have to introduce a couple which is equivalent to the force moment produced by that particular force. So we are introducing the couple. So all the 7 couples are acting clockwise, anti-clockwise, and horizontal, vertical forces are acting. Now that is tabulated here. Okay, so the first part, the resultant is obtained. This is the single resultant force and single or the resultant couple that is acting at this foremast point. The second part is replacing all the 4 tugboats. If you are using only one tugboat, okay, where on the hull, okay, the boat will be pushing the ocean liner. That is the second part. For that, we have found the x-intercept, the y-intercept of the line of action of the force. How do we obtain the line of action of the force? We release the couple from this point, so we shifted the force away, finding out the distance d. Okay, this is the distance. Then finding out y-intercept and x-intercept to find out the x point on the hull, because we know the y point, right? That distance is 12.4 meter. I hope this is clear now.
This is another problem in 3 dimension. We will see this problem. What is asked is 3 cables are attached to a bracket as zone as shown. Replace the forces exerted by the cables with an equivalent force coupled system at A. So what is asked is, there are 3 forces acting on the bracket. Okay, so replace all the forces, okay, with an equivalent force coupled system. So move all the forces to A and introduce the couples. Okay, that equivalent force coupled system is asked. Okay, now we can see that the position vector of all the 3 forces from A. So position vector of B with respect to A, position vector of C with respect to A, position vector of D with respect to A are given here, and it is very straightforward. Now this vector magnitude is given, the inclination is given, and it is in xz plane, and it will have 2 components. Okay, and this component is x component and that component is z component. Similarly, this is lying in xy plane, and this angle is given, this angle is given, this is cos 60, this is cos 30. We can straight away get x y direction. But here if you see B, the magnitude is given and it is inclined to all 3 axes, and the force vector we have to find, because the coordinate point, the other coordinate point is given, B coordinate point is known, and this is taken as x1, y1 and z1. This is taken as x2, y2, z2, and that is given as this vector. So lambda vector we have to find in this line. Lambda vector is the position vector divided by the magnitude. So that is the magnitude. So for the lambda vector, how do we find out? Under the square root, 75 square, 150 square plus 50 square, that leads to 175. So we find FB vector. So we know this vector components, we know the component of this vector, and we have got the components of FB vector. So FC vector, this is referring to z-axis. FD vector, so this is k vector. The small mistake is a k vector for C. Since this is the z-axis, this component is in this direction, okay, that is negative z, so it is k vector. If you see this is x vector, x direction, and this is y direction, so this should be k vector. And now what is the question asked? You have to find out the resultant vector. You know all the three vectors, FB vector, FC vector, and FD vector. So you just add all that, there will be a resultant vector, and each vector about A will produce moment. So the resultant moment, we have to add all these vectors about A. So first the force of B about A. So the position vector cross F vector, determinant ijk, these are the coordinates of B vector from A, and then these are the components of force FB. So Fx, Fy, and Fz, we get this vector. Position vector of C with respect to A, right? Position vector of D with respect to A, cross FD vector, is just substitute the coordinate points and the force vectors. Here it is clearly given. Now it is in the Z direction, so we'll be able to find three vectors. Just add all those three vectors, we get the resultant. Now at A, see the resultant force, x direction positive, y direction positive, z direction negative, so it is in this direction because positive is here in this direction, so it is negative. Similarly, we get mx is positive, so anti-clockwise, we are using anti-clockwise, that is magnitude is 30. 17 is also positive, so anti-clockwise. This is also positive about z-axis, that is also okay, anti-clockwise. So we have represented all the forces about A. So we moved all the forces to A and we introduced the moment, but it is represented in terms of rectangular coordinates. So if at all to represent R vector, it will have a particular direction. We'll put that, and all these three vectors resultant will be in one particular direction. Okay, so that way the net effect can be represented. So reduction of all the forces to A without affecting the net effect is understood. I hope you would have understood this concept in a better way. We'll see the next concept in the next lecture. Thank you.